Can empty space be used to generate thrust? That is the provocative question behind vacuum polarization engine theories, which propose that motion could arise by interacting with the quantum vacuum itself. According to quantum field theory, what we think of as empty space is not truly empty. It seethes with virtual particles flickering in and out of existence, a phenomenon known as vacuum polarization. The idea is that under certain conditions, applying energy or electromagnetic fields might distort this vacuum and create a tiny real force, potentially enough to generate thrust without expelling mass, violating the expectations of classical Newtonian mechanics. But how could this actually work? Theories like the controversial EM drive or quantum vacuum plasma thrusters suggest that by shaping electromagnetic fields in a cavity or device, it's possible to create an imbalance in vacuum fluctuations, essentially pushing against the quantum foam. Some fringe experiments have claimed to detect minute thrusts under controlled conditions, though the results are often at the edge of measurement error and remain highly debated. Analogy, it's like trying to sail a boat without wind or oars, just by pressing against the ripples of space itself. While mainstream physics remains skeptical, vacuum polarization engine theories challenge our understanding of inertia, energy, and the very nature of nothing, suggesting that motion might be possible through the quantum fabric of the universe itself. How can one harness distortions of the quantum vacuum, a sea of fluctuating virtual particles, to generate net thrust or motion without expelling reaction mass? Vacuum polarization engine theories propose that by asymmetrically manipulating electromagnetic fields or boundary conditions, one might induce a non-uniform vacuum stress akin to the Casimir effect and convert it into usable propulsion. So far, so good, until we confront the clash with fundamental conservation laws. In principle, the vacuum's zero-point fluctuations permeate all of space symmetrically. Any local distortion, for example by moving or shaping conductive boundaries, produces forces that are internally balanced. Efforts to break that symmetry, such as pulsing electromagnetic fields in cavities or dynamically altering mirror separations, inevitably require input work equal to or greater than any observed thrust, leaving no net gain once boundary reactions are accounted for. At its core, these theories rely on vacuum polarization, virtual electron-positron pairs momentarily screening applied fields, altering the local permittivity and permeability of space. If one could engineer a time-varying asymmetry, for instance, by modulating a resonant cavity's geometry at high frequency, the altered vacuum stress tensor might produce a directional pressure differential. Initial calculations suggest tiny unidirectional forces, but detailed analyses reveal that corresponding reaction forces on the driving apparatus cancel any net momentum transfer to the external world. Yet even this more nuanced view hides deeper challenges. Quantum field theory enforces Lorentz invariance and momentum conservation at every interaction vertex. Any vacuum fluctuation exploited for thrust must, when treated consistently, exchange equal and opposite momentum with whatever is generating the field distortion, be it mirrors, coils, or dielectric materials. Proposed reactionless drives like the EM drive, which claim anomalous thrust from microwaves in a tapered cavity, have repeatedly failed to demonstrate unambiguous, repeatable net forces once careful null tests and thermal expansion artifacts are controlled. At even finer scales, renormalization and gauge invariance ensure that vacuum polarization contributes only to observable effects when tied to real charge or boundary conditions. Attempts to extract free energy or momentum from the vacuum bump into the same no-go theorems that forbid perpetual magmission machines. The vacuum's energy density may be enormous in theory, but it is not a reservoir one can draw from without paying the price in the form of equal and opposite stress on the manipulator itself. In essence, vacuum polarization engine theories spotlight the seductive promise of the quantum vacuum as a new reaction mass, yet they ultimately reinforce the universality of conservation laws and symmetry principles. The vacuum may teem with ephemeral energy and polarization effects, but, like other profound paradoxes, from hysteresis loops to quantum retrocausality, It reminds us that the deepest insights of physics lie in the inviolate balance between action and counter. Vacuum polarization engine theories propose that energy can be extracted from quantum vacuum fluctuations to generate thrust without propellant. These theories build on the concept that the vacuum is not empty, but teems with virtual particle-antiparticle pairs that can be polarized or unbalanced under strong fields. By dynamically altering boundary conditions or field configurations, one aims to create a net exchange of momentum with these fluctuations, producing motion. This challenges the classical notion that propulsion always requires ejecting mass. The dynamic Casimir effect has been demonstrated in superconducting circuits by converting vacuum fluctuations into real photons when boundary conditions oscillate. It is like rippling a calm pond's surface with a vibrating barrier to push tiny droplets outward, harnessing the water itself for thrust. Classical propulsion relies on Newton's third law by ejecting reaction mass backward to move forward, such as rockets expelling exhaust gases. Vacuum distortion propulsion instead seeks to asymmetrically perturb the zero-point field, effectively pushing against the fabric of space itself. While classical engines consume fuel and produce exhaust, vacuum engines would ideally draw on omnipresent vacuum energy with no mass loss. This fundamental shift redefines reaction mass as the vacuum field rather than onboard propellant. A photon rocket ejects light for thrust but still requires onboard energy and generates recoil. Vacuum engines aim to tap ambient vacuum energy directly. It is like sailing without wind or water by tilting the boat's hull to interact with unseen currents beneath the keel. Quantum field theory describes the vacuum as a ground state with transient virtual particles that pop into and out of existence on femtosecond timescales. When an external field is applied, these virtual pairs become polarized, aligning momentarily before annihilating, which changes the local energy density. Engine theories propose to cycle these fields to create a directional imbalance in polarization pressure. Repeated cycles could, in principle, sum to a measurable macroscopic thrust. In strong electric fields, vacuum polarization contributes a tiny correction to molecular energy levels, known as the Lamb shift. It is like briefly aligning countless microscopic magnets in one direction to create a weak but cumulative magnetic push. The static Casimir effect arises from the attraction between two uncharged closely spaced plates due to vacuum mode suppression between them. The dynamic Casimir effect extends this by moving one boundary rapidly, converting vacuum fluctuations into real photons. Vacuum engine concepts envision oscillating cavity geometries or modulated electromagnetic fields to produce a directional photon flux. This flux imparts momentum to the cavity, yielding thrust without traditional reaction mass. Experiments with superconducting circuits have observed photon generation when the effective electrical length of a cavity is modulated at gigahertz frequencies. It is like shaking a box of ping-pong balls at just the right frequency so that balls gradually eject in one direction, pushing the box the other way. Extracting usable energy from vacuum fluctuations requires breaking time symmetry in field excitations to prevent immediate reabsorption of virtual particles. Engine proposals incorporate non-reciprocal materials or time-varying boundary conditions to bias the emission of real quanta. Achieving net energy gain hinges on carefully engineered resonance and impedance matching with vacuum modes. If successful, these methods could tap the enormous reservoir of zero-point energy. Theoretical models suggest that metamaterials with time-varying permittivity could preferentially emit vacuum-directed photons in one direction. It is like converting background radio static into a steady stream of directed sound by using a smart antenna that amplifies certain frequencies. Some experimental claims of reactionless thrust, such as M-drive tests, assert momentum generation without propellant, possibly via vacuum interactions. Critics argue that observed thrusts fall within measurement error or arise from thermal and electromagnetic artifacts. Nonlinear coupling between fields and the vacuum could, however, produce subtle forces that elude conventional calibrations. Rigorous replication with null force controls is essential to distinguish genuine quantum vacuum effects from spurious signals. Independent tests of the EM drive at NASA's Eagle Works lab reported micronewtons of thrust but subsequent experiments with improved shielding found no net force. It is like hearing a barely audible hum from a silent speaker system. One must rule out echoes and feedback before attributing it to a new audio technology. If vacuum polarization engines proved viable, spacecraft could achieve high specific impulse and long missions without carrying massive propellant reserves. On Earth, stationary platforms might tap zero-point energy for local power generation. The ability to manipulate vacuum energy directly would revolutionize both transportation and energy sectors. However, such breakthroughs also demand rethinking energy regulations and reactor safety paradigms. A successful vacuum thruster could reduce interplanetary travel time from years to months by providing continuous low-thrust acceleration. It is like discovering a wind that blows everywhere all the time, enabling ships to sail indefinitely without refueling. Detecting tiny forces from vacuum interactions requires sub-micronewton precision and elimination of thermal drifts, electromagnetic coupling, and seismic noise. Theoretical models must reconcile energy momentum conservation with non-equilibrium vacuum dynamics, avoiding violations of relativity. Many proposed mechanisms remain speculative without consensus on mathematical rigor. Establishing a clear, reproducible signal correlated with vacuum modulation is the key hurdle. Prototypes using high-Q resonant cavities report ambiguous thrust signals that vanish when rotated or when control experiments are performed. It is like trying to prove a new musical instrument produces sound in total silence. You must ensure no stray vibrations or drafts are influencing your ears. Advances in metamaterials, ultrafast optics, and quantum nanomechanics may enable stronger coupling to vacuum modes and clearer thrust signatures. The development of theoretical frameworks that integrate dynamic Casimir effects with general relativity could predict optimal engine geometries. If validated, vacuum polarization engines would reshape our understanding of spacetime, energy, and motion. Ultimately, exploration of these theories may uncover fundamental insights into quantum field theory and the nature of the vacuum itself. Proposed experiments using superconducting metacavities aim to measure directional photon emission correlated with mechanical oscillation. It is like tuning a violin string in interstellar space to resonate with the cosmic microwave background, hoping to hear its subtle vibration as proof of a deeper universal harmony.